Let's continue with our analysis of a BJT amplifier. And we left off last video having calculated what the total base current is, total meaning the DC along with the AC portion. And we saw that by adding the AC signal, it causes this sinusoidal variation around the Q value. Well, continuing on now and finding the total collector current, well, the collector current, the total, it's still beta spec times IB. So here it's beta spec times IB total. So we just take our equation here for IB total, multiply it by 100, which is our beta spec, and we come up with that the collector current will also have a sinusoidal variation around its Q value of 780 microamps, where this positive peak would be approximately, well, it would be equal to 780 plus 49.5 microamps. So that's 829.5 microamps. And then this negative peak would just be the 780 minus the 49.5. So it would be, what, it'd be 730.5 if I did my math right. Alright. So then continuing on, the V out total, not VC, this is V out. Okay, the V out total would just be the same expression as we had for the Q value, but now IC total instead of just the DC value for IC. So we're going to get our, oops, this is a mistake here, isn't it? This V0 here, this is VCC minus what we have. Oh, well, no, I'm just showing, I'm sorry, this is right. I'm just showing the what this comes out to. If you take VCC of 15 and then subtract, putting in RC of 10K and then plugging in this expression here for IC total and then working it all out, it comes out to what you see here, that you get the Q value of V out, the 7.2 that we had before, minus this sinusoidal term here. So the total V out, sorry for the typo, the total V out is going to look like this, where you have this negative sign centered around the Q value of 7.2 volts. So this peak here, positive peak, would roughly be 7.7 volts, right? Because it's going to be 7.2 plus 0.495. And then this negative peaks, the negative peaks would be roughly 6.7 volts. Okay, 7.2 minus 0.495. Now notice that unlike the current curves here, where the sinusoidal variation was a plus sign, here the sinusoidal variation is a negative sign. So since Vn, if we look back at Vn, see, Vn was a positive sign, so it started on the positive peak, the positive half cycle, I should say. Where this is minus sign, V out starts on the negative half cycle. So you see, with this type of amplifier, you'll have a 180 degree phase shift between V out and V in. Okay, so if VI, like in this example, starts on the positive half cycle, your V out will start on a negative half cycle, and vice versa. Alright, so that's the effect of the AC signal on our waveforms. Now, here's the real key point, is that, you know, the whole purpose of this circuit is to amplify the AC signal at the input. So to see that it's done that, and by how much amplification we have this measure called AC gain. And this is just V out over V in, the AC portion. Okay, we're looking at the AC. Right? Oops. It's just AC. Okay, AC gain. So the input signal, again, let's go back. See, the input signal, we can either take its peak value, which is 50, or we can take its peak to peak value, which is 100 millivolts. Okay, but let's just take the peak. Okay, so see, this here would be 50 volts peak. And since we're using peak for VI, we'll do the same thing for V out. Then now if we look at V out, see here's our peak AC at V out. It's this 0.495, which is the same as 495 millivolts. Actually, I forgot to put the milli here. This 50 is milli. Right? So you see 495 millivolts peak. See, when you're doing AC gain, you got to have both the numerator and denominator in the same unit. So if you're going to use volts peak for V in, you got to use volts peak for V out. If you use peak to peak for V in, you got to use peak to peak for V out. You got to keep those the same. Otherwise, you're going to introduce a factor of 2 error. So now you can see that the AC portion at the output, okay, the AC sinusoid at the output is roughly 10 times larger than the AC that we had at the input. Now, this AC portion at the output, it's centered on 7.2 instead of 0, right? Because the input AC was centered on 0. But that's okay, because it would be very easy if we had to. If we needed to get rid of this 7.2, we could just pass this signal through a coupling capacitor, and the capacitor would allow the AC portion through while blocking that DC Q value. Okay, if we chose to do that. Sometimes you don't even care that AC is centered on some other value other than 0. Okay, so that's the whole purpose of this circuit, is that this circuit is amplifying that sinusoid at the input by almost a factor of 10 at the output. Alright, last thing here is I want to talk about an important limit on V out, and that's this statement right here. Okay, that V out can never be more than what your VCC is, and it can never be below ground for this type of amplifier. And that's because on the output side of the circuit, okay, the collector side of the circuit, well, that's the DC energy that we're supplying, 15 volts. Also, we're not supplying a negative voltage for this amplifier. So because we're not supplying a negative DC voltage, that's why V out can never be negative, so it can't be below ground, which is 0 volts. And because the largest, or because VC has a value of 15 volts, V out can't exceed that. See, if V out were to exceed this positive voltage source value that we're supplying at the collector, VCC, that would be a violation of conservation of energy. Okay, because remember, voltage is an indication of the amount of energy needed to move current between two nodes. And see, this is the this is representative of the DC energy that we're presenting to the circuit in order to power the transistor, in order to get the amplification of the AC signal. But no portion of that AC signal can be greater than what we're supplying. Again, it would be like getting more energy out than what we're putting in. So what this means is that if you were to increase your input voltage, your input sinusoidal amplitude, like say we were to, double V in from 50 millivolts to 100 millivolts, well, V out will also double, okay, because AC gain is a constant, that there'll always be this factor of about 10 in this example between the V out peak, the V out amplitude, and what V in is. So you see, as I increase the input amplitude of V in, V out is going to be proportionally increasing the same amount, and always about 10 times bigger than V in. So there's going to be a point, if you increase VI enough, there's going to be a point where the sinusoid is going to hit up against a limit. Now, because this 7.2 is closer to the lower limit than the upper limit, our amplified signal, our amplified AC signal, would hit ground before it hits VCC, right? It's going to hit this 0.3 volts sooner than what it hits up here. But you see, once the output signal hits against a limit, it becomes what's called clipped. It's going to flatten out at that limit. And once you get a flattened signal like that, it's called a distorted waveform, okay? Because it's not at that point a pure sinusoid anymore, right? Because now it's got a flat portion towards it. And a lot of times you don't want that to happen, because that will cause distortion of the information that the signal represents. So in most cases you don't want distortion. I mean, there are some examples like, you know, distortion amplifiers that musicians use where they intentionally distort the signal, but in most cases you don't want to distort a signal like that. So we can come up with what's called the maximum undistorted output. Okay, and again, we're talking about AC here, so the answer to this will always be either in peak or peak to peak. And in this example here, this maximum undistorted output would just be equal to 7.2 volts peak. Okay, or 14.4 volts peak to peak. Okay, PP is just short for peak to peak. See, if this Q value was right in the center, 7.5, well then we would have the largest maximum undistorted output possible, right? Because in that case, if this output sinusoid was centered on 7.5, it would hit both of these limits at the same time. You know, another quick one, if this Q value was, say, 10 volts, well then a maximum undistorted output would be 5 volts, because it would hit the upper limit before it hit the lower limit, right? If this sinusoid was centered at 10, and remember this sinusoid's symmetric, so it's going to be increasing the same amount on the positive half cycle as the negative half cycle, well, it would hit VCC a lot sooner than it would hit ground in that case. Okay, so that's how you figure out maximum undistorted output. And then there's figuring what the input is, what the input is for the max undistorted output. Okay, so often, you know, once you know what the maximum undistorted output is, you want to know, well, what input voltage corresponds to that maximum undistorted output. And to answer that question, you just take your maximum undistorted output and divide by the AC gain, because again, your AC at the output is always related to your AC at the input through the factor of the AC gain. So for this example here, we would just take either 7.2 volts peak, or we could take the 14.4 volts peak to peak and just divide by the AC gain. Okay, 9.9, and I'm going to approximate that as 10. So, you know, our answer in peak would just be 0.72, and in peak to peak it would just be 1.44 volts peak to peak. Okay, so you should hopefully be comfortable with calculating either of these two, the maximum undistorted output or the corresponding input.